Welcome to the fascinating and critical world of adversarial machine learning. I'm thrilled to guide you through one of AI's most important security challenges. Imagine this. You're driving in a Tesla and someone places a tiny sticker on a stop sign. Suddenly, your car's AI thinks it's a speed limit sign and doesn't stop. This isn't science fiction. It's adversarial machine learning in action. Adversarial machine learning is the study of attacks against machine learning systems and the defenses to protect them. Think of it as cybersecurity for AI models. Just as hackers exploit vulnerabilities in traditional software, adversarial attacks exploit the mathematical vulnerabilities in neural networks. What makes this particularly dangerous is that these attacks can be imperceptible to humans while completely fooling AI systems. The fundamental problem lies in how neural networks learn. They create complex, high dimensional decision boundaries that separate different classes. But these boundaries have blind spots, tiny regions where small, carefully crafted changes can cause massive misclassifications. It's like finding secret passages in a maze that the AI never learned to guard against. Let's explore the main types of adversarial attacks. Evasion attacks are the most common. They modify input data to fool a trained model during inference. Think of adding noise to an image to make a classifier think a cat is a dog. Poisoning attacks contaminate the training data itself, causing the model to learn incorrect patterns from the start. Model extraction attacks steal intellectual property by querying a model and reverse engineering its behavior. The attack taxonomy gets more specific. White box attacks assume the attacker has complete knowledge of the model architecture, weights, and training data, like having the blueprint to a building before breaking in. Black box attacks work with limited information, only accessing the model's outputs, more like trying to pick a lock without seeing the mechanism. Gray box attacks fall somewhere in between with partial knowledge of the system. Let's dive into famous attack methods. Fast gradient sign method, FGSM, was one of the first. It calculates gradients to find the direction that maximally increases the loss function, then takes a small step in that direction. Projected gradient descent, PGD, is like FGSM but iterative, taking multiple smaller steps. Carlini and Wagner attacks are more sophisticated, optimizing for minimal perturbations while ensuring successful misclassification. Beyond images, adversarial attacks work across all AI domains. In natural language processing, researchers have created sentences that look normal to humans but completely confuse sentiment analysis models. In speech recognition, they've embedded hidden commands in music that activate voice assistants without humans noticing. Autonomous vehicles can be tricked by adversarial traffic signs, and medical AI can misdiagnose X-rays with carefully crafted noise. The defense strategies are equally fascinating. Adversarial training involves training models on adversarial examples, teaching them to recognize and resist attacks, like inoculating against a virus. Defensive distillation creates smoother decision boundaries by training models to output probability distributions rather than hard classifications. Input pre-processing techniques like denoising, compression, or transformation can remove adversarial perturbations. Detection-based defenses focus on identifying adversarial inputs before they reach the model. Statistical tests can spot unusual patterns in input data. Ensemble methods use multiple models with different architectures. If they disagree significantly, it might indicate an attack. Certified defenses provide mathematical guarantees about model robustness within certain bounds, though they often sacrifice some accuracy. The arms race between attacks and defenses is ongoing and fascinating. Attackers developed adaptive attacks that specifically target known defenses. Gradient masking can hide gradients from attackers, but often creates false security. Obfuscated gradients make it harder for attackers to find adversarial examples, but sophisticated attackers can often work around these defenses. It's a constant cycle of innovation on both sides. Real-world implications are profound. Autonomous vehicles must be robust against adversarial signs and objects. Medical AI systems need protection against adversarial attacks that could cause misdiagnosis. Financial AI faces adversarial attacks in fraud detection and algorithmic trading. Content moderation systems must resist adversarial content designed to bypass safety filters. The stakes couldn't be higher. Current research frontiers are pushing boundaries. Physics-based attacks create adversarial examples that work in the real world under different lighting and angles. Universal adversarial perturbations create single noise patterns that fool models across many different inputs. Adversarial patches are physical objects that can be 3D printed and placed in the real world to fool computer vision systems. Building robust AI systems requires a security-first mindset. Always assume your model will be attacked. Implement defense in depth with multiple protection layers. Red team your AI systems by actively trying to break them. Monitor and log model behavior for unusual patterns. Remember, adversarial robustness isn't just about technical defenses. It's about building trustworthy AI that society can rely on. In our next session, we'll implement hands-on adversarial attacks and defenses to see these concepts in action.